Hi everyone, welcome to the Measurement and Density Lab. This is where I'll show you how to do every part of the lab. I'll show you important things to remember about the procedure, about what you need to submit, and then you'll just do the lab at home. I'm assuming by now that you've all picked up your chemistry kit, so you've already got a big thing crossed off your list. Nice work. So I'm going to share my screen, and here's where we are. Measurement and densities. So we're going to take what we learned previously about measurements and how important significant figures are, and we're going to apply it to a lab in order to calculate density of different substances and to just make sure that we're recording measurements properly. So here we are, and you have already prepared. You've got everything you need, most likely, right? Make sure that you're reading through. Every week, you'll see lab materials of exactly how to prepare and how to get credit. So make sure that you don't forget to submit your photographs of you picking up your chem kit. So your chem kit with a number on it, as well as a picture of you having signed your name next to your numbered chem kit on the sign out sheet. That's how you'll get your full credit for picking up your chem kit today. All right, so let's see what I want to show you. The only thing, so all the instructions are here on how to get credit. The only thing that is different between my two classes for how to get credit is that Chem 1A students, you'll need to write a conclusion following the record keeping guidelines above right here. And Chem 2, you don't have to write a conclusion yet. But everything else is pretty much similar. And then the only difference is you'll see for Chem 1A, there's an extra part in the actual lab itself that you'll see when you do the lab. In Chem 2, there's one part that's taken off. And also the post-lab questions are different as well. So let's get started. I want to start by showing you the actual lab and make sure that you read everything thoroughly. So every lab you're reading through at least twice, at least 3 times, and imagining yourself doing the lab itself so that you can feel comfortable once you do it. And you learned what density means. It's an intrinsic property, meaning it doesn't matter how much of the substance you measure, it's always going to have the same density. And we learned how to calculate density. Density is equal to mass over volume, or as we learned, we can draw a heart to remember, right? M over V. All right. So you're reading the procedure. And so for part one, we're going to do together. We're going to take some general measurements and paying attention to the precision of the measurement, because remember, we don't want to lie. We don't want to tell lies about how precise our measurements are, because the precision is only afforded by the actual instrument itself. We can't say it's more precise or less precise than it actually is. It really is important. We don't want to tell lies. So we're going to do part one all together. And then what we'll do is trial one of part two together, and then you'll do trial 3 and 2 together at home with your chem kit. And then we're going to do trial one of part three. We're going to do trial one of part 4A and B together. And for Chem 1A, we'll do part 5 at the end. All right, so here's the template. Remember that you needed to write out in your lab notebook right here. And the template is always going to, or rather, I should say, in the template, you'll see how to set up your laboratory notebook. And that's what you'll always do before you start a lab, is prepare your laboratory notebook so that you can do the lab either with me or with Terry later on in the semester on video, or with your chem kit at home. So you're always going to write the date, write the title and the purpose. And for this one, you're literally just copying the template exactly for this lab, okay? So you're literally copying the purpose and the data tables. So for part one, this is what I'm going to be writing in, just like you'll be writing in your lab notebook. All right, so let's begin. For part one, we're going to take some general measurements of different samples. What we're going to do is I'll write them up here before I show you. We are going to be measuring water 4 different times. We are going to be measuring a penny as well. So those are the samples. And the properties measured for the water are going to be volume 3 times. We're going to measure the temperature of the water too. And we're going to, for the penny, measure its distance, so the diameter, as well as the mass. And so now the measuring devices that we're going to use are 3 different measuring devices for volume. The first one's going to be a 50 milliliter beaker. We use a little hyphen between the number and the unit of a measurement when it's an adjective. So we're like describing the beaker, right? It's a 50 milliliter beaker. If we were just measuring 50 milliliters of water, we don't need the dash, we don't need the hyphen because it's not describing the water, it's just the amount of water. Okay. So a 50 milliliter beaker. We're also going to measure the water using a 50 milliliter graduated cylinder. As well as a 10 milliliter graduated cylinder. These are all glassware that you have in your kit. You're also going to measure the temperature using a thermometer. You also have one of those, a thermometer, and a ruler. You'll need to find a ruler. So remember, you can find one either in your home if you have one, you can print one out. You can use one on your phone. Just make sure that it's accurate, that it like measures your screen resolution and your screen size. But yeah, as long as it's a metric ruler, you can use it. And the mass. So we're going to use a digital scale. All right, so let's begin taking some measurements. I'm going to stop share and move my camera over to the side real quick. All right, so here we are. First, we said we're going to measure the volume of water in a 50 milliliter beaker. And again, we have to pay really close attention to the precision of the instrument. So this instrument is the 50 milliliter beaker. And I'm going to try to get it, see if it can get a little more focused here. Sometimes it does, sometimes it doesn't. But the main important part of the water that we're measuring is it the top of the meniscus or is it the bottom of the meniscus? Are we measuring here or here? Bottom or top? Right. It's the bottom. We're always measuring the bottom of the meniscus when we're measuring a liquid, specifically water, in a measuring device. Let's see if we can get that sharper. All right. Okay. So it doesn't look like I can get it more focused right now, but that's okay. So when we have our readings here, we've got a beaker that has graduation marks at 30 milliliters and 40 milliliters. There's no in between. And remember that the first estimated digit is the last digit that we report in a measurement. So we know for sure that there's at least 30 milliliters in the beaker, but we don't have any numbers in between telling us that it's 31 or 32 or 33, etc. So we have to guess. We have to estimate the level of the bottom of the meniscus in between 30 and 40. So that is the last digit that we can report. So we know it's 30. And then what do we think? The bottom of the meniscus, making sure that we have some, a surface behind the beaker, kind of blocking the light. What do we think? 30 what? Sure. I would take 34. I would take 35. but not 34.5 because remember, we're estimating the 4 or the 5. We are estimating 34 or 35. So why don't we just say, let me see, I'll say 35. Oh yeah, there we go. That's nice and sharp right there. Okay, we'll say 35 milliliters for that measurement. 35 milliliters. What I'll do is show you after we're done taking all the measurements down, make sure you write them down, but I'll show you my template, from my lab notebook online when we're done. All right, so 35 milliliters for the 50 milliliter beaker. Now we're going to measure the volume of water in a 50 milliliter graduated cylinder, right? Graduated, meaning there's lines, there's measurements, there's indication of the volume, right? And it's a cylinder, right? Because it's long and skinny and cylindrical. All right, so now, right, we're still going to be measuring to the bottom of the meniscus, but now we've got extra lines. Here's 10 milliliters right here. Here's 20 milliliters right here. And remember, we always want to be at eye level. So I've set this up so that the bottom of the meniscus is at camera level. So that's what we want to, okay, at eye level. All right, so we know for sure there's 10, 11, 12, 13, 14, 15, 16, 17 milliliters, right? Because that's what the lines tell us. 17, now we're gonna read between the lines. And when we put our hand behind there, can we see that the very bottom of the meniscus is just below that line right there? Right? It's just below this line right here. So we know it's 15, 16, 17. What? What do we think? 17. What do we think? Sure. 17.9 sounds good to me, right? Because we're estimating between these two lines. We know for sure it's 17 because that's where the line tells us that it is, and in between, and it's almost at the 18 mark. So we'll say 17.9 for the water in this 50 milliliter graduated cylinder. 17.9 milliliters. All right. So as we'll see later, if it were exactly on this line right here, if this meniscus bottom was exactly on that line, what would we say? It's a little below. If it were exactly on the line, right, we would say 18, not just 18, but 18.0, right? So that 0.0 tells us that the instrument is precise to the 10th of a milliliter. And in our measurement that we got 17.9, that's also telling us that the instrument is precise to the 10th of a milliliter. So when it's on the line, we still have to represent that precision. If it were on this line right here, we would say 18.0, but it's a little bit low, so we'll say 17.9. All right, now we've got our 10 milliliter graduated cylinder. And let's see, so that to me, what does that look like to everyone? You know what I want to do? I want to make this just for teaching purposes. I'm going to just dab out a teeny tiny bit because I want it to be on the line so I can have that to show you. Just dab out a little bit. Maybe that'll be all right. All right. Maybe, maybe not. I want teeny, tiny. Bear with me, please. Okay, so here we are, my 10 milliliter graduated cylinder. And what do we report this volume as? Right, exactly. 2.0, right? Now, this bottom of the bottom of the meniscus is exactly on the line, right? So we report that as 2.0 milliliters. So these 10 milliliter graduated cylinders that you have in your lab kit report they can be measured to the 10th of a milliliter. Let me show you what I mean when I pour just a teeny bit more water in here, because you might not be exactly on the line. You kind of still are, but that's okay. There we go. It's getting a little bit higher now. All right. So check it out what I mean, right? If this were a little bit higher, we'd have 2 point, how many are each of these lines worth? How many milliliters are each of these lines in between worth? We've got 2, we've got 3, right? Each one of these is worth 0.2 milliliters. So here's 2.2, 2.4, 2.6, right? And now we're estimating, so that looks to be about like 2.7, right? But we can't go any further out than that because that's the first time that we are estimating the digit. So these graduated cylinders aren't as precise as other 10 milliliter graduated cylinders. You're still only going to be able to report the 10th of a milliliter. So the measurement that you write down, though, is the one that we had before that was exactly on the line, 2.0. Okay, so both of these graduated cylinders that you have in your lab kit, the 50 mil graduated cylinder, right? 50, and the 10 mil graduated cylinder, 10, are precise to the 10th of a milliliter. Alrighty, now we're measuring the temperature of the water. I've got my thermometer here. So what do we say? How many degrees Celsius am I measuring here for the water? Right? We've got, we know it's at least 20, and here's 30 up here. So each of these little marks is worth 1 degree Celsius, right? So we know it's for sure 20, for sure 21, right? Now we have to estimate between the 21 and the 22. So what does that look like to you? Sure. I would say like 21.7, right? And it's actually heating up a little bit as I'm holding it on the bottom there. So yeah, about 21.7 degrees Celsius. And that's what we'll write down. All right, now we are measuring the diameter of a penny, the distance of a penny, the diameter, and I've got my metric ruler lined up, right, with centimeters. So I'm measuring in centimeters, and that's what you all want to measure in today too, okay, when you do your at-home part. So this ruler happens to have a 0 at the very edge of the ruler, right? This is 0 right here. But some rulers have a 0 that is a little bit in from the edge. So make sure that you're just paying attention to your ruler. See what I mean? I've got 0.1, 0.2, 0.3, 0.4, 0.5, right? Starting from the edge. So just make sure you're paying attention to your ruler. All right, so we're gonna measure the diameter. I'm gonna line up the very edge of my ruler because that's my 0. Getting the diameter. And what do we say? What is that measurement here? What do we think? We know it's at least 1 centimeter for sure, right? We know it's at least 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8. And to me, when I line up the very end of the ruler with the edge of the penny, that hits just before the 1.9, right? So I like to say that this diameter is 1.89 centimeters. See what I mean? The edge of the penny is just before the line. And so see how precise you have to be? Like you can't just, oh yeah, that's 2 centimeters. No, 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 no. We got to look really carefully and be really precise with our measurements. And that end of the penny to me is just before the 1.9 line. So I'm going to write 1.89 centimeters for my diameter of the penny. All right. So one more, we're going to measure the mass of a penny. You're going to turn on your scale, and you can decide whether you like the light or not. I'm going to turn it off. I believe it's easier to see on the camera, right? Either way. Let me see if I can get that brighter. Okay. So your scales work like this. Well, I'll show you after actually. Let's just get the mass of the pennies. So it's on 0. Make sure that you have a 0 mass on there. If it's not on 0, you would push tare, right? The T stands for tare, and that just zeros your balance. So let's get the mass of a penny. All right. And this tells me that 1 penny has a mass of 2.51 grams. So that's what I write down. If it said 2.50, if there was a 2.50 there, what would we write down? Exactly, we would write down 2.50. So every digit in a digital readout is a significant digit, and so we write down all the digits. All right, so let's make sure we write down all our measurements correctly. Our 50 ml beaker was 35 milliliters of water. Our 50 ml graduated cylinder was 17.9 milliliters of water. Our 10 ml graduated cylinder was 2.0 milliliters of water. Our temperature of the water was 21.7 degrees Celsius. The ruler measured a distance of 1.89 centimeters. And the digital scale read a mass of 2.51 grams for the penny. All right, so now we're going to continue and move on to part 2. We're going to measure the density of the water. And so who knows what the density of water should be? Right? Should be close to 1 gram per milliliter. All right, so that means that's what you can look for today. All right, so let's see. We are going to measure the mass of the water and the volume of the water in order to calculate the density, because remember, density is equal to mass divided by volume. So we're going to do these steps. We're going to determine the mass of the cylinder and the water. Well, first, what we need to do is look back over here at how we determine the density of the water. Let's look back at the procedure. We're going to dry a 10 ml graduated cylinder and measure its mass, right? And then we're going to pour about 9 milliliters of water into the cylinder and carefully read the volume. I've crossed out to the nearest 0.01 mil because actually, remember, your 10 milliliter graduated cylinders only measure to the precision of a 0.1 milliliter or a tenth of a milliliter. Now we're going to weigh the cylinder plus the water, right? And determine the density of the water. Okay, then you're going to do it at home. You're going to do it at home with the graduated cylinder, the 10 ml graduated cylinder, and then you're going to try it at home with a beaker. Okay, and you're going to figure out which of these trials is the most accurate, right? Which of the trials has the least uncertainty, and tell me why in your post-op questions. Okay, all right. So here we are with our graduated cylinder right here. So what I'm going to do is dry it. And what you can do is take some paper towel, right? A long piece of paper towel, and you can, right? You can take a long piece of paper towel and fold it, right? And then kind of twist it so that you get a nice long piece of twisted paper towel that you can dry out your graduated cylinder with. All right, so I've got my graduated cylinder. I'm going to dry it by twisting it inside. Take it out. I don't know why I'm blurry here. Let's see. There we go. Come on. Hello. And actually, turn this around. Okay. Okay. I've got it focused. And again, we got our dry graduated cylinder. Now I'm going to measure the mass of the empty graduated cylinder, turning on the balance. Right, letting it settle. And again, I'm going to turn off the light. I think you can see it better that way. There we go. And measure your mass of your empty graduated cylinder. So 34.67 grams. And then it said to add about 9 milliliters of water. So I will do that. About 9 milliliters of water. So why do you not need to add exactly 9 milliliters? What's more important instead? Think about that. What's more important than adding exactly 9 milliliters of water? Right. What's more important is that you actually write down the precise volume, okay? And that you get the actual mass. It's not as important how much is actually in there. It's more important that you write down the correct measurement, okay? So I'm going to bring this down. Let's read this volume here. Remember what we learned before, right? We want to make sure that we read the bottom of the meniscus at eye level. And so we know we have at least 9 milliliters. We know we have at least 9.2. So what do we think? It's below the 9.4 and above the 9.2. So the best we can do with these graduated cylinders is say 9 point what? Right, the bottom of the meniscus. Right, 9.3 milliliters. That's our volume. So 9.3 milliliters is the volume of the water. And now we want to measure it again. We're going to turn on our balance again and measure the mass of the cylinder plus the water. So for me, the mass of my cylinder plus the water is 43.87 grams. All right, so I'm going to take us back to share my screen and we'll write this all down. In our lab notebook. All right, so the mass of the cylinder plus the water, that's the first measurement written down here, but it's the last one that we take. It's the first one written down because when we write this down, 43.87 grams, all we have to do is subtract the mass of the cylinder to get the mass of the water, right? So 43.87 minus 34.67 will give us the mass of the water. So 0, 2, 9.20 grams is the mass of the water. And then the volume of the water we recorded as 9.3 milliliters. All right, so that's our trial one for the density of the water. Why don't we just do the density calculations now while we have it fresh in our mind? So for trial one, right, density is equal to mass over volume, which is equal to the mass of the water, 9.20 grams, divided by the volume of the water, 9.3 milliliters. What do we get? 9.2 divided by 9.3 is equal to 0.989, etc. But we need to make sure that we round to the correct number of significant figures, right? So how many significant figures do we have in this number right here? Right. There's just two significant figures here. How many significant figures are in this number, 9.20? Right. There's three significant figures here. So we need to round our answer to the fewest significant figures, right? Because this is division. So 0.99, and we need to keep these units of gram per milliliter. And make sure that you then write this up here for your calculated density of water, 0.99 grams per mil. All right, we have two significant figures because we don't want to lie and record our final density with more significant figures than the instruments provided. All right. So now we'll go down to the percent error calculation. We're going to use our expected theoretical value of the density of water as 1.0 grams per milliliter. And we look in the lab at the bottom at the workup, right, the data analysis, the percent error is calculated by subtracting theoretical value from the experimental value and dividing by the theoretical value, absolute, right, value of that times 100%. So here we are. Let's calculate the percent error for trial 1. So this is equal to, or percent error is equal to the experimental value. So that's 0.99 minus 1.0 divided by the theoretical value of 1.0. And this is going to be absolute value. And we're going to, that's absolute value. We're going to multiply by 100%. All right, so get our calculator back up here. But here's the deal. This is a calculation that involves multiple steps. So 0.99 or minus 1 gives us 0.01. We take the absolute value of that, right? And so this, we have to pause right here. So that gives us 0.01 divided by 1.0 times 100%, right? Let's make sure that we do the subtraction, right, with the correct number of significant figures. We have to round, if we rounded at this step right here with the subtraction, we would have to round to the place that's the least precise, right? That's the rule for subtraction. The least precise place in these two numbers is the tenths place. So this place is where we would have to round to, right? And then when we do the division, if we rounded to this place here, that would be 1 sig fig. So now in our division, we will assume that we take these two digits, which would be one significant figure right here, and then our final answer, therefore, will also just have one significant figure. So times 100 gives us a 1% error. Okay, I'm going to repeat that. This is subtraction, which follows the rule of the least precise place needing to round, right? We would have to round to the least precise place, which would be this place here. The tenths place is less precise than the hundredths place. So that's why I underlined this place. We would have to round there if we ended the calculation there. But since we're now doing division, we have to take into account, and I'm just gonna, right? Since now we're doing division, we have to take into account this one digit here, right? That would be the one precise digit, which would be one significant figure, right? So that means that our final answer needs one significant figure as well. Okay, so try that on your own on your trials and see how you do. All right, everyone. So that's what we do for part 2. Just make sure that you take a picture, right, of your setup for this part so that you can include it in your submission for your lab. All right. Now we'll move on to part 3. We're going to calculate the density of a saline solution, meaning a salty water, right? A saline solution is sodium chloride dissolved in water. So now we're going to use the same method that we used for part 2, but we have to make the saline solution. So hopefully you have obtained your table salt from home or wherever you shop to get some table salt. And what we're going to do is tear a 50 milliliter beaker, add 14 grams of salt, add 40.0 milliliters of water, and we're going to stir it to completely dissolve it. Okay, make sure that you also take pictures of this part. So I'm going to walk you through that. All right, so this time we're going to tear a 50 milliliter beaker by first turning on the balance. And be very careful with these balances because they're super sensitive. If you spill anything on them, wipe it off right away, please. And never overload it. That's super important as well. But with the things that we have to work with today, you shouldn't have to worry about that. Okay. So when it says to tear a 50 milliliter beaker, it means zero it. We're zeroing it on the scale. We push T for tear. And now the mass of the beaker is kind of already accounted for, rather it's kind of it's subtracted from the mass of the salt already. So this time we don't have to do any subtraction when we're making our saline solution. We can just add the sodium chloride right to the beaker. Okay, so I've got my table salt zeroed out. I'm going to add 14.0 grams to make a saturated sodium chloride solution, meaning it's saturated with salt. The water cannot absorb, the water cannot hold any more salt. It has the maximum amount of salt dissolved in the water. Get it up to 14 grams. And I know I said 14.00, but just do the best you can, okay? It doesn't have to be, I wanted it to be really similar for everyone, so get as close as you can, but if it's not, if it's 14.01, that is okay. So I'm almost there. Woo. There we go. 14.00 grams of table salt. And now we're going to add 40.0 milliliters of water. So what am I going to do? Am I going to just fill up this beaker to the 40 ml mark? What do we think? Right. No, Oh, that wouldn't be adding 40 mils of water. That would just be making the whole solution have a total volume of 40 mils of water, right? And it wouldn't be 40.0. So what I'm instead going to do is use my 50 milliliter graduated cylinder. So making sure to measure out 40 milliliters of water in my 50 milliliter graduated cylinder. 40.0. Right. That is close enough. I could add a couple more drops of water to make sure the bottom of the meniscus is right on the line. And that's pretty darn close. Yep. Eye level, right? Bottom of the meniscus is right on the 40. And I'll add it to my salt in my beaker. All right. And likely you'll need some heat to help dissolve. Okay. So what you'll do, you can use your thermometer, just be really gentle with it. Okay. Please be careful because this glassware, it'll just be a hassle for you if anything breaks. So what I also recommend is to, if you're on a hard surface, like if your floor is tile, you know, or if you have like a tile hard surface tabletop, I recommend laying out a towel on the floor, laying out a towel on your workspace so that there's a soft landing if anything should drop. And so you're going to keep stirring, but you'll likely need some heat. So just like it says in the instructions in the procedure, what you'll do is take your beaker and you can put it in the microwave for 10 seconds. Bring it out, stir it a little bit more. Take it, put it in the microwave again for 10 seconds, right? Beep, bring it back. And you should, at that point, have, you should at that point have a nice and dissolved saline solution. I don't have the full volume anymore because I've used this before and I've used some already, but you should have a nice clear solution, okay, after you've microwaved it twice and stirred it. All right, so that's what I'm going to work with now. Okay, so you're going to use the same procedure that you used before for determining the density of the water. You'll make sure that you dry out your graduated cylinder that you used before. So I'm going to pour it into my waste container. That's a good idea too, is to have a waste container so that you don't have to keep getting up. And I'm going to dry it using my twisted paper towel again. And it's the same procedure. So we want to measure the mass of the empty graduated cylinder. And remember that we're following the procedure right here, right? So using the same method that we did before. And what did we do? We dried a 10 mil graduated cylinder. We measured its mass. We poured about 9 mils of water. But again, for this time in part 3, you're not going to add water. You're adding your saline solution. All right. And then you'll get the volume of the saline solution and then the mass of the solution plus the cylinder. All right. So I'm drying out my cylinder. Dry them outside too. All right. You see some water, I see some in there. I want to kind of get that out. All right. Because we want to make sure that we account for, right, all the volume that's in the cylinder, we want to be accounted for in the mass. So we need to make sure that we get an empty mass to do that. And I've got a little bit of debris on my scale, my balance. I'm going to wipe it off a little bit. All right. So we've got it on 0. Turn off the light so you can see. I got my empty graduated cylinder again. And this is for part 3, trial 1. So empty 34.68 grams. And then we're going to add our about 9 milliliters of our saline solution that you just made. We'll bring this down so we can read the volume. There we go. Okay. So what do we think? Let's get this right about eye level here. And to me, the bottom of that meniscus, let's see, it's definitely above the 9.2. And so in this case, once again, we kind of just have to do the best we can at estimation. We can't say 9.25 or 9.22 or anything because we're already estimating once we get above the 9.2. Okay, so we know for sure it's 9.2 and it's in between these two. So it's not 9.2, it's not 9.4. The first time we're estimating, it has to therefore be the 9.3. Okay, so again, our volume will be 9.3 milliliters. And let's get the mass of the cylinder plus the saline solution. I'm going to turn off the light again, make sure that it's at 0, which it is. And now we've got a mass of 45.54 grams. All right, and let's make sure that we record this on our notebook. Okay, so mass of the cylinder plus the saline solution was that last mass that we just got, which is 45.54 grams. The mass of the empty graduated cylinder was 34.68 grams. The mass of the saline solution, therefore, when we do the subtraction, is 45.54 minus 34.68, which gives us 10.86, a lot heavier, right, than before. And the volume was still the same, 9.3 milliliters. All right, so let's do this density calculation. We know that density, right, again, is equal to the mass over the volume, which in this case is 10.86 grams divided by 9.3 milliliters. And again, let's take into account our significant figures. We've got 4 sig figs in the mass. We've got 2 sig figs in the volume. And so when we do this division, 10.86 divided by 9.3, we got 1.677, etc. Oh, wait, let me see. 1.16, right? 1.1677. Let's make sure. Right. And now we need to round because it's division to the fewest significant figures. So 2 sig figs. So let's do that. 1.2 grams per milliliter. Let's make sure we write that in our final table. 1.2 grams per milliliter, and that's just about what the density of a saturated saline solution is. I'm not going to have you calculate the percent error, but That's okay. Okay, so I just realized up here in your density of water where you're calculating the um, percent error, I had you use 1.00 grams per milliliter as the theoretical density of water. So let's actually go back to our calculations and make sure that we take that into account. And actually, you know what? Let's do it the other way around. I'm just gonna change this instruction right here to 1.0. Okay, everyone? So you'll use 1.0 grams per milliliter as your theoretical density of water. So you can just use that for each calculation for the percent error. All right, everyone. So now we're going to go on to part 4. And for part 4, I want to make another change too. It says that you'll need 10 to 15 pennies, but in reality, I know it's kind of hard to come by. So why don't we just say 5 to 10 pennies instead? And that's what it says on the instructions in the lab materials page on Canvas. So you'll need your scale, you'll need your metric ruler. And again, you can find a metric ruler online, print it out, or use it on your phone or your computer if you don't have one. And then you're using your 50 milliliter graduated cylinder. Okay, so we're going to do it 2 different ways. First, we're going to calculate the volume of the pennies, of a stack of pennies, using the equation for the volume of a cylinder, because what we can do is measure the diameter and the height of the cylinder of a stack of pennies. And then we're going to do it with water displacement. Okay, so in part B, what we'll do is instead we're going to get the volume of water, right? We're going to get a volume of water. We're going to add the pennies to that water and then record the volume again and subtract in order to determine the volume of just the pennies. And I'll show you how to do that, okay? Again, don't forget to take a picture of each. You don't have to take a picture of each step. You can just take a picture of this part. All right. So let's move back over here. Okay. And we're going to, and make sure, oh, and just be careful that they are all post 1982 pennies. So it should be easier to find, you know, newer pennies than older pennies anyway. And so make sure that they're all post 1982, because in 1982, something changed with the way pennies were made. And we'll see how we can tell if they're pure copper or not. All right, so we're going to determine the density from linear measurements first. So we're going to get the mass of our pennies, right? Because again, we're determining the density of the pennies. And so we'll need the mass and the volume. In part A, we get the volume by linear measurements and calculating the volume of a sphere. And in part B, we get the volume from water displacement and just subtract the difference in volume once we add the pennies to a certain volume of water. So we're going to get the mass of the pennies, and we can use the same mass for both parts. So we'll do that first. Here's from linear measurements, we'll get the mass of the pennies. All right, so I've got 10 pennies here. And I'm going to get the mass of my 10 pennies. The mass of my 10 pennies is 26.30 grams. And so let's write that here. 26.30 grams. Okay, and we already got the diameter of 1 penny. I'm just going to use the diameter of the 1 penny that we measured in the beginning. Okay, 1.89 centimeters. All right, now we're going to use our measurement skills to determine the height of the stack of pennies. I'm going to take them off here. And the trick to doing this is what you can do is line up your pennies on the edge of a surface. Let's see if we can do that here. All right, so we've got the edge of our surface here, the edge of our table. We've got all 10 pennies. We want to line it up on the edge so that then we can use the ruler, right? Because again, my ruler, like I showed you, it has the 0 at the edge of the ruler, but yours might not, right? Yours might not. And so if you need to, you'll just move the ruler down, right, to get to the edge of a stack of pennies. Mine, I can just measure from the table, right? Because the 0 mark is the edge of the ruler. But yours might not be, is what I'm saying, right? So let me see if I can get this a little off, but we'll do our best. Okay. I'm trying to line up, make sure you can see. Okay. So what do we say the height of this stack of pennies is? Let's make sure that we're looking at this edge right here, right? And where it lines up to the ruler. We know it's at least 1. Here's our 1 mark down here, right? 1.1, 1.2, 1.3, 1.4. So what do we say? Where does the edge of that penny line up right here? 1.4, 1.42? What do y'all say about that? Right, 1.42 looks about to me. Okay, so that's the height of my penny stock. All right. So what we'll do is now calculate the volume. So we saw on the actual lab itself that we can use the volume of a cylinder to calculate the volume of the pennies, okay? So volume is equal to pi times the diameter over 2 squared times the height. So let's do our volume calculations over this side. Volume is equal to pi times the diameter over 2, so the radius squared times the height. And so let's plug everything in for our trial 1, which we just did. So we've got pi times the diameter over 2, so 1.89 over 2. And we're going to square that first and then multiply that by the height of 1. And let me actually place in my units there so we can keep track. So 1.89 centimeters divided by 2 squared times 1.42 centimeters, which is the height, right? So let's get our calculator. So let's do this. We've got our pi button somewhere. Right here, right? Pi times, let's do parentheses, 1.89, close parentheses, and squared. Oops, let's not do that. See, it depends on your calculator, right? So I'm going to do it step by step, in fact. I'm going to do 1.89 divided by 2 equals, and I'm going to square that. Okay, and then multiply by pi equals, and then I'm going to multiply by 1.42. And so the volume of my stack of pennies is 3.9838, etc. And what's my unit here, everyone? What's my unit? We know it's going to be centimeters something. Look, we've got centimeters squared times centimeters. So what unit is that? Right, cubic centimeters, right? Which makes sense. That is a unit of volume. All right, cubic centimeters. And now for the density calculation, right? We've got density again is equal to the mass over the volume. We're going to take this volume. We're not going to round it yet. We're going to keep it long in our calculator. We're going to divide the mass, 26.30 grams, divided by 3.9838 cubic centimeters in our calculator here. So 3.983839. So 26.30 divided by 3.983839, etc. And that gives us a density of 6.6016 grams per cubic centimeter. Let's make sure that we round to the proper significant figures, right? So in this number, we've got 4 significant figures, right? Over here, how many sig figs should we have? How many significant figures should we have in this number here? Let's look at this one. There's 3 sig figs, right? And this one, 3 sig figs. So we should also keep 3 sig figs. So this number should have 3 sig figs. We just haven't rounded it yet so that we don't introduce rounding error. And so our final answer should also have the fewest significant figures, so 3. So 6.60 grams per cubic centimeter. So the calculated volume of the pennies rounded was 3.98 cubic centimeters. And the calculated density of the pennies, mass over volume, is 6.60 grams per cubic centimeter. All right, so you'll do that with your trial too at home. And that's how we determine the volume of, or rather the density of pennies using linear measurements. And we don't have to divide by 10 pennies or anything because we already accounted for the fact that there were 10 pennies in the stack, right? We got the mass of 10 pennies and the volume of 10 pennies. Therefore, once we do that division, the density of the 10 pennies is the same as the density of just 1 penny. So we are going to now do part B, density from volume displacement. So using water displacement. All right, so this time we will just add some water. We're going to add some water to our 50 milliliter graduated cylinder. It doesn't have to be very much. The important thing is just that we record the volume precisely. Maybe 20 something milliliters. That should be just fine. Bring it down here. All right, so let's just make sure that we record the volume. Precisely. All right, so the bottom of that meniscus, we know that it's at least 20, right? 21, 22. So in between the lines, what do we think? 22 point what? we just kind of imagine that that would be 22.5 right in half. So maybe 22.7? What do you think? 22.7 milliliters works for me. So in our data table, right, we're going to have our initial volume of water. So this is part B, density from volume displacement. So we're going to have initial volume of water, 22.7 milliliters. And we have our mass of pennies. We can just use that from the other part, 26.30 grams. And now we're going to add the pennies to the graduated cylinder. But you're going to do it very gently. You're going to tilt the graduated cylinder and slide them in. Tap out any water bottles, water bubbles, air bubbles, right? Gently. All right. And now we're going to get the final volume of the water and then subtract. And that's how this time we're going to determine the volume of the pennies from water displacement. All right. So now the bottom of that meniscus to me is exactly on the line. Let's see what it looks like actually. Yeah, exactly on the line. And so how do we report this volume right here? What is that? 20 what? Yep. If you said 26.0, you are correct. So 26.0 milliliters here for the final volume of the pennies in the water. And so now we're going to just subtract, right? We're going to use the same method that we did in the first parts for just obtaining the mass of the water. Now we're using it to determine the volume of the pennies, okay? And so 26.0 minus 22.7 milliliters gives us a volume of 3.3 milliliters. All right, so that's now our volume of pennies using the displacement, water displacement. And so now we've got density is equal to mass over volume. That was easier this time, right? To determine the volume. And so we've got 26.30 grams for the pennies divided by the volume, 3.3. And so we do this math. $7.96969. All right, and make sure, right, that we round to the proper significant figures. We've got 4 significant figures because remember that zeros at the end of a number with a decimal point are significant. We've got 2 sig figs because these are both non-zero numbers. And so our final answer has to be rounded to 2 significant figures. So how do we round this to 2 sig figs? Right. The 6 would round up the 9, which would round up the 7. So we get 8.0 grams per mil. Be careful that you're paying attention to the units, right? In this case, the density units for the pennies, right, are grams per milliliter because we measured the volume using the graduated cylinder, which measures milliliters, okay? So 8.0 grams per mil. Okay, so Chem 2 folks, that's where you will end your experiment after you do your trials 2 for all of the parts. And so Chem 1A people, come with me. We'll continue to part 5. All right, so in part 5 for Chem 1A folks, you are going to determine the volume of a drop of water, which is pretty cool. This time, we're not going to be measuring the density of a drop of water. We are going to be using the density of water to calculate the volume of a drop of water because we can rearrange the equation for density to do that. We saw that up here, right? Density is equal to mass over volume, which means that volume is equal to mass over density, right? So that's what we're going to be solving for in part 5 is the volume. All right, pretty cool. And it's also cool because it's really tiny, right? And we wouldn't be able to measure the volume of just one drop of water using a graduated cylinder because it's too large, the graduated cylinder, and the drop is too tiny. So we can use a different method to do so. So it says you want to use a small container. So I'm just going to use my beaker. I recommend using your beaker. And first you want to practice drawing some water into a pipette and dispensing drops until you make drops of the same size. You're going to add 30 drops of water to your container and weigh it, but make sure that you get the mass of the empty container first, right? Okay. So I don't have that up there, but oh no, it does. It says, never mind. It does say right here that you need a small container, right? Weigh the container to the nearest 0.01 grams. So we're going to do that first. Then we're going to practice making drops of the same size. We're going to add about 30 drops of the water to the container and weigh it again, right? And then we're going to get the mass of 30 drops of water by subtraction. We're going to divide to get the mass of 1 drop of water. And then we'll use the density of water to calculate the volume of 1 drop. All right. And so let's do this here. Okay. So we're going to get the mass of the empty container. And again, I just recommend you use your beaker here. Make sure that you clean it and dry it. And so the mass of my empty container, this beaker, is 28.23 grams. And now I've got my pipette, right, with some water that I have drawn into the pipette. And I'm just going to practice making drops of the same size on this enamel metal surface. You can use a plate or something. So when I'm making the drops of the same size, I want to make sure that I am dropping vertically. This is the standard delivery technique. Okay, I'm not dropping horizontally like this because that leads to inconsistent drop sizes. I'm dropping vertically. And I want to make sure that the drop does not touch the surface before it completely comes out. So you're practicing making drops of the same size. And these are looking pretty good. Okay, so just practicing. You can draw more water into your pipette. Over on the side over there, right? And just make sure that maybe you fill it up to about that line right there where it says 2 milliliters. Then you'll know you'll have enough. So I'm going to wipe away my drops of water that I did for practice. And again, you want to get the same size drops so that your average drop mass and therefore drop volume is more accurate. All right. So I'm going to turn on my balance again. And now I'm going to add my 30 drops of, as best I can, the same volume to my cylinder. So here I have 28.22. So what I think I'm going to do is actually tear this, or we'll just do it this way, actually. I'm going to turn it off. I'm going to add my 30 drops of water so that the balance doesn't turn off, because sometimes the balances turn off in the middle of weighing and it can be frustrating. So instead, I've already got my mass of my empty beaker. Now I'm going to add my 30 drops of water. Make sure you just count. It doesn't have to be exactly 30 as long as you know how many. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. All right. So now I'm going to weigh my beaker plus the 30 drops, working quickly because we don't want it to evaporate. And now 29.47 grams. Okay, so let's get this down on our lab notebook. Container plus 30 drops, 29.47. Grams. Make sure that you're writing down your units everywhere, okay? Mass of the empty container was 28.23 grams. And for the mass of just the water, we've got to subtract again 29.47 minus 28.23, 1.24 grams. And then we've got, that's the mass of 30 drops of water. So the mass of 1 drop of water, we're just going to divide by 30. This is grams per drop. Oops. Grams per 30 drops. So if we divide that out, 1.24 divided by 30, we get 0.0413 grams per drop. And that's per drop of water. And I rounded it to this many significant figures because look, we've got 30 drops here. That is an exact number, right? We counted that number of drops. So that's not a measured number. So the sig figs do not play into it because it's like having infinite sig figs. Here, there's 3 sig figs from the mass. And so now I've got 3 sig figs here, grams per drop. And this is what I will write in my mass per 1 drop, 0.0413 grams per drop. Right. And now I've got my density of water. And so I can use the density to calculate the volume of 1 drop of water. Right. So now I'll take this 0.0413 grams per drop. I'm actually going to set it up like we know how, or like we will know how, grams per drop. And what we can do is multiply. We can use the density, right, to get grams on the bottom so that they cancel out in milliliters on top. That way, grams will cancel because whatever is on top, if it's divided by something over here, just like in math, if you've got 5 on top of an equation divided by 5, they cancel out. If you've got grams on top divided by grams, they cancel out. So that's 1.00 grams per milliliter. And in that way, we can cancel out. So this means then that since the density, right, and this is the density of water, right? Since the density is 1, this means that the number of grams per drop is the same as the number of milliliters per drop. So 0.0413 milliliters per drop. So that is what we write up here. And that's very small, right? We wouldn't be able to measure 0.0413 milliliters in one of these graduated cylinders. So that's why it's really useful to be able to use the density of water to calculate volume if we know the mass. All right, hope you're with me still. And we've just got one more part. Let's calculate the number of drops in 1.00 milliliters of water. So now we've got 1.00 milliliters of H2O. We want to calculate the number of drops per milliliter, right? We've got this many milliliters per drop. So let's place this into the calculation. Now what we'll do, this is 0.0413 milliliters for every one drop. So we're going to put the milliliters on the bottom so that milliliters cancel out, and we'll have it for every one drop on top, and that's going to allow us to calculate the number of drops. So 1 divided by 0.0413 gives us 24.213 drops per milliliter, but let's make sure that we round to the proper significant figures. So there's 3 significant figures here, 3 significant figures here. So let's round to 3 significant figures in the final answer, 24.2 drops per milliliter. Good to know. 24, just about, drops in a milliliter. That's really useful if you all enjoy making, using essential oils. It's useful to know how many drops of essential oils are in a milliliter so that you can mix, right? Make blends with lotions and stuff and lip balms. That's what I've done before, and it's really useful. So 24.2 drops of water in 1 milliliter. It's going to be different for oils because oils are more viscous and less dense. And so you'll get a slightly different number, but that's what we have for water. So there you have it, everyone. You'll do the same thing for trial 2 at home. Thank you so much for tuning in. And again, I'm available if you're doing this lab during regular lab hours. I'm available on Zoom, so I'll see you there. Make sure you work with your partner and have fun. And I'll see you soon. Thanks a lot.